that it doesn't include 0 since you divide by 0.
Oh, right. In fact, you're right. It does not include 0. 0 is, in fact, a singular point of that differential equation. All right. So what I want to try to describe to you guys now is what does it mean for a differential equation to have a singular point? All right. Oh. Hey, wait a minute. Where's King? We got nobody to man the lights today. So it's okay. We might not even. I will. When it's time, I'll do it. While I'm waiting for my computer to come back to life. Yep, that's the answer. Yeah, that's the best we can do here as a series solution. So, see if I can't get this working here. So in my notes, of course, I do have a rundown of the. These are the ones you guys are supposed to know from Calculus 2, right? And I come across some of them today in the examples, but I didn't hit all of them. And I guess we'll, if you guys don't mind, let me get my laser. The projector in here is kind of weak. Otherwise, I'd keep some lights on. It's just it's not quite good enough. It seems like it's kind of. It doesn't seem green. It seems kind of overly blue. But anyway, so these are now you guys. At this point in the course, this shouldn't be terrifying to you because I've also told you something else about the next test, which is what? You get a sheet of paper, right? Yeah, so you might, unless you know these, right? But writing these and using them on slightly modified problems is also a little bit different. You probably need to review power series. Most people do here. Oh, look, there's the inverse tangent. Oh. What am I doing? Oh, interesting. Sorry. It's the way I wrote it there. It was kind of weirding me out. Here's some examples. Oh, look. Planned this. No, actually, I didn't. I just made this up today. It just happens to be the ones in my notes. Sorry, I'm not giving you a lot of variety and resources, but here's the typed up version of what we just went through. For fun, you can see if I did the calculation exactly the same way or not. I don't know, maybe it's not that fun. But did we come to the same answer? Uh-oh. Huh. What did I do? Huh. Yeah, I think it's the same answer, but I've quote-unquote simplified the coefficients here. Right? So it's sometimes possible to take like the answers that we came to over there. If you play with them for a bit, you can see how to factor out a. Well, can you? Sorry, I should have skipped past this. It's too late though. What's going on here is if you start looking at this, you can start counting 4s. Here's a 4. There's a 2 times a 4 here. There's a k times a 4 here. If you start looking at it, you got a bunch of 4s. And paired with those 4s, you have numbers that are counting down to 1. In other words, you got 4 to a power times k factorial. So if you just group all of those, you can reconvert it to a 4 to the k times k factorial. And that's what's left over. Just the 11, the 7, and the 3. Which is just 7 and 3 here. And likewise over here, you can peel off a 4 and a k factorial and leave just part of the product. So which is the better answer? I don't know. Is this really better than that? I guess beauty's in the eye of the beholder or something. But see, beauty. Say beauty's only formula deep. Is that right? It's here. It's here. All right, come on. Here we go. Finally, what I'm looking for. Now, get the lights again. All right, so we say x naught is an ordinary point. So, by the way, these things we're doing could be done for third order or first order or fourth order with not much modification, but almost all of the applications people are interested in are second order, so our focus is on second order differential equations, right? So we say x naught is an ordinary point of y prime prime plus py prime plus qy equals to 0 if and only if p and q are analytic at x naught. What's that mean for p and q to be analytic at x naught? What that means is that they have a power series expansion at x naught. In other words, it means they don't misbehave at x naught. All right? So if we look at, for example, this is awful. So if we, oh man. So if we look at the Cauchy-Euler problem, this thing, right? Something like ax squared y prime prime plus bx y prime plus cy equals to 0. There's your sort of generic Cauchy-Euler problem, right? That's not in the right format yet to judge whether or not it's singular, or to judge whether or not it has an ordinary point or whatever. To fix it, we get something like y prime prime plus what? B over ax y prime plus c over ax squared y equal to 0. Now it's got the right format. See, this is my quote-unquote big P. This is my quote-unquote big Q. And these are what? These are analytic away from where? Away from x equal to 0. If I picked any other point besides 0, all right, every point except for 0 is an ordinary point for this differential equation. So if I try to find power series solutions at 0, I get in trouble. All right? So 0 is a singular point for the Cauchy-Euler problem. It's actually what's called a regular singular point. King! See here. You're fine. You're fine in my exercise. See here. So where is it? Yep. So if these are analytic, it's an ordinary point. Otherwise, it's a singular point. It's a regular singular point if it's a singular point. However, x minus x naught times p of x and x minus x naught squared times q of x are analytic. All right. So let's look at that. Look at that Cauchy-Euler problem again. Let me show you why it's a regular singular point. So what is x times? So x naught here is 0. X naught equals to 0, singular point. And check it out. X times p. What's that equal to? X times b over ax. So that's just b over a. And x squared times q is what? C over ax squared, which is just what? C over a, right? So assuming that a, b, and c are constants and a is non-zero, these are constants. They're certainly analytic. Constant functions are analytic. What's the power series for a constant? These are the power series for the constant. I mean, that's it. So the Cauchy-Euler problem has a regular singular point at 0. It's the easiest kind of regular singular point problem that you can solve. Let's see if I got some examples here. Here's a good example. e to the x and cosine x are analytic, it follows the differential equation y prime prime plus e to the x y prime plus cosine x y equal to 0 has no singular points. Because its coefficient functions they're analytic everywhere. So there's no singular point for this problem. You can use power series methods to find a solution centered about any point you want, and it will work out. In contrast, if we look at this problem, x squared plus 1 y prime prime plus y equal to 0, well, again, this isn't quite in the right format yet, right? I have to divide by x squared plus 1 to get to the right big P, big Q format. Then I've got y prime prime plus 1 over x squared plus 1 y equal to 0. All right. Now, you might think that 1 over x squared plus 1 is everywhere analytic, but you'd be wrong. I mean, well, that's the thing. We have to understand 1 over x squared plus 1 in the terms of its complex factoring. We have to look at singularities in the complex plane. All right? So, well, how can I say this? It is true that every real number, that this differential equation is everywhere. Every point is an ordinary point for this differential equation because the coefficient function 1 over x squared plus 1 is analytic everywhere for the reals. However, unlike the first example, there's some kind of fine print attached. We're not going to expect a solution to exist for all reals because actually this 1 over x squared plus 1, it hits the plus or minus I in the complex sense. But anyway, I'm getting ahead to a theorem that I need to state here in a minute. So this one also has no singular points in the real sense. But it does have singular points in the complex sense. All right? So plus or minus I are complex singular points here, you could say. Y prime prime, here we go. 1 over x squared times x minus 1. Now this one has trouble at 0. And it has trouble at 1. Right? And this guy has trouble at 1 and also 2 plus or minus I if you complete the square there. Now if we look at x times p of x, we get this. So it's not a regular singular point because x times p of x is not analytic at 0. So 0 is an irregular singular point for this one because x times p of x is not an analytic function. I think x equals to 1 is a regular singular point here, though, because if we look at x minus 1 times p of x, we get these clear out, and you're just left with 1 over x squared. That is analytic at 1. You can find a power series expansion for that at 1. And x minus 1 squared q of x gives me that, which again is analytic at 1. So this example has 0 as an irregular singular point, but 1 as a regular singular point. Come on. So here's the theorem, the big theorem. If we have a solution of y prime prime plus py prime plus qy equals to 0, centered at an ordinary point x naught, all right, can be extended to an open disk in the complex plane which reaches the closest singularity. A solution of y prime prime plus py prime plus qy equals 0 based at a regular singular point x naught extends to an open interval with x naught at one edge and x naught plus or minus r on the other edge, where r is the distance to the next nearest singularity besides x naught, of course. So what this is actually, let me just put it into words. What it says is that if you're solving a real differential equation at a regular point, all right, at an ordinary point, a point where the coefficient functions are analytic, your solution will extend as far as the differential equation is well behaved over the complex numbers. If there's a singularity for your differential equations in the complex number system, then if you look at the disk which is defined between your center and that complex singularity, that will put a limit on how big the domain can be. And something similar is said about the regular singular point. Now I'll draw some. I usually spend about 20 minutes a class like actually visualizing this theorem. So next class I'll start with probably some examples to actually flesh out what I'm saying right now. So thanks, guys.